All right, thanks for having me. All right, so I'm excited to be here and telling you a little bit about the stuff that I research. What I want to tell you about today is a model of the universe known as the lambda CDM model. This model has been so successful at describing observations of the universe that it's emerged as the standard cosmological model. However, there are all alternative ideas about exactly how structure forms in the universe, and I'm going to tell you a little bit about those as well. And I'm also going to tell you about how we're testing these models using a unique data set known as our local universe. All right, so in the standard cosmological model, you can break up the mass-energy budget of the universe into 3 components, 70% of which is in this mysterious form of energy known as dark energy. And this dark energy is driving the accelerated expansion of the universe in our recent history. About 5% is ordinary matter, or normal matter. This is the stuff that makes up galaxies, stars, planets, you, me, protons, neutrons. And when I say normal matter, I mean the properties and the interactions of that matter can be described by our standard model of particle physics. Most important for the purpose of this talk is normal matter interacts with light electromagnetically. So normal matter absorbs light, it emits light, it scatters light. You can see me right now because the light bulbs that are made out of normal matter are emitting light. That light is scattering off of me. It's entering your eyeball, which is being absorbed, and your brain is processing it as an image, right? These are all of the functions and the ways that normal matter behaves, which leaves about 25% in the form of dark matter. So in the standard cosmological model, we generally like to think of dark matter as a massive particle. It's a particle that's about 100 times the mass of a proton, and it interacts only through gravity and the weak force. And so what's most interesting about this is that it doesn't interact with light in any way. It doesn't absorb light, doesn't scatter light, it doesn't emit light either. That's the last one I was missing. Light particles will just pass right through a dark matter particle. This dark matter particle is interesting to to particle physicists. We had a great talk last month by Jan Killick, a professor at UT in the physics department, who told us all about the particle side of this and why he's interested in it. It's interesting because this is a particle that wasn't predicted by the standard model of particle physics. So this is something that requires some new physics to explain how it's produced in the early universe. We have no idea where it comes from, and we actually don't know exactly what its properties are, and we'll come to that a little bit later in the talk. Another fun fact about dark matter is that it's so weakly interacting that every second, millions of dark matter particles are passing through your body every second. And so that's how weakly interacting, because none of you noticed until I just mentioned it. All right, dark matter is interesting to me because it plays a really vital role in the formation of structure in the universe. This is actually what leads to the formation and evolution of galaxies. So I love this slide because this is the entire history of the universe in one image. There it is. And I'm going to give you a rundown of it in a couple minutes. So here we go. So the universe, about 13.7 billion years ago, springs into existence. And at the beginning, it's a very hot, dense, energetic soup of elementary particles. As the universe expands, it's going to cool. And as it cools, eventually quarks can get bound up together to form protons and neutrons. Again, the universe is going to continue to expand and continue to cool. It's going to keep doing that over and over and over again. And as it does that, the protons and neutrons will eventually fuse together to form nuclei. Eventually, those protons and those nuclei will be able to capture free electrons that are floating around and form neutral atoms. At that point, the primordial photons, particles of light that have been ping-ponging around between these electrons, are able to free stream throughout the universe. And it's at that point, 380,000 years after the Big Bang, we have this imprint of this baby universe in the cosmic microwave background, and those photons stream throughout, reach us today, and we can collect those, and we have this amazing data set of this beginning stage of the universe from the cosmic microwave background. It's a whole talk in of itself, and hopefully we'll find someone to come and give it. I'd really like that. All right, so at that point, the universe enters a period known as the Dark Ages. So this is the period before the first stars form in the universe. So during this period, dark matter halos are collapsing. In the standard model, dark matter halos form hierarchically. It means that the low mass, small dark matter halos form first, and then they merge to build up larger dark matter halos. During this time, these dark matter halos, as they're collapsing, they're also dragging in gas, and that gas falls in, it can cool, and eventually form stars. So the first stars form about 400 million years after the start of the Big Bang and end the Dark Ages. And these first stars are forming in the first galaxies. Galaxies also form hierarchically in the standard model. Low mass, small galaxies known as dwarf galaxies form first and then merge and build up our larger galaxies like the Milky Way that we live in today. So in the intervening 13 or so billion years, galaxies are merging, they're growing larger galaxies. Eventually, dark energy kicks in and drives an accelerated expansion, and here we are today. So there you go, history of the universe, all in a couple minutes. All right, the key takeaway from this is that in the early universe, these dark matter halos, as they collapse, these are forming the seeds that galaxies will form in. And so I just threw a lot of terms at you, a lot of ideas, so we're going to kind of give you a simple summary slide and give you some definition of terms. So again, in the standard model, we think of dark matter as this massive particle. It's known as a WIMP, a weakly interacting massive particle, because it only interacts through gravity and the weak force. What's important for our talk, and this will come back later, is this type of dark matter is known as cold dark matter. And that's because when this dark matter was produced in the early universe, it was produced with a small intrinsic velocity. All right, so this is a very cold type of dark matter. And this dark matter gravitationally collects in dark matter halos. You're going to hear me say that term a lot, dark matter halo. And basically what you can think of as a dark matter halo is this is just, it's kind of a gas of dark matter particles that are gravitationally bound. All right, so when you think of a dark matter halo, it's just this sea of dark matter particles that are swirling around. All right, and those dark matter halos are important because they're the sites where galaxies will form. So they're gas on the outskirts, it's going to get dragged into the center of these dark matter halos in this simple cartoon, eventually cool and form stars. All right, and this is what's interesting for us, because this is the way we can go about probing the nature of dark matter using astronomy and astrophysics. You can actually, because we know that dark matter halos are the sites of galaxies, we can learn something by studying the large-scale properties, the large statistical properties of galaxies out in the universe in surveys, and learn something about the nature of dark matter. So how do we go about doing this in the lab or on computers, which is what I do? We can run these numerical simulations. So what we're going to do is we're going to take a bunch of virtual dark matter particles in a computer and put them in a box and watch them gravitate. All right, so each blue or cyan point in this is a dark matter particle, a virtual dark matter particle in a box. The box is meant to represent a large volume in the universe. And what we do is we initially distribute them so they mimic the early conditions of the universe. So you'll notice that roughly there's roughly equal amounts of matter in all portions of this box, and that's because the universe on large scales is homogeneous and isotropic, which means that it's the same no matter what direction you look in everywhere in the universe. On small scales, though, there's little bits of overdensities. There are little overdensities where there's a little extra bits of matter, and there's a little underdensities, little portions where there's a little less matter than average. And those are going to be critical because that's going to be what drives our eventual structure formation. If this was totally homogeneous, nothing would ever collapse. It would all just stay smoothed out. But because we have little extra bits here and there, eventually dark matter halos will form, and you'll see that in a second. All right, so what we do is we put all these particles in a box again. We set them up so they mimic the early conditions. And then we calculate the gravitational force of each particle on every other particle. All right? And then once we have the forces calculated on every single particle in this box, we know how the particles should be moving, and we could take a step forward in time. So this Z up here is basically a demarker of time for our purposes. And so this is very, very early in the universe, about 200 million years or so after the start of the Big Bang. So we take a step forward, and we begin to see stuff, gravitational instability start to work. So in the portions where we had a little extra bit of matter, dark matter particles are pulled in to these little overdensities, and the baby beginnings of dark matter halos are starting to form. So now we repeat the whole thing. We calculate the gravitational force of every particle in this box on every other particle, and then we take another step forward. Another step forward, and we repeat this over and over again until we reach 13.7 billion years later, where we are today, and this is what we get. So you're beginning to see dark matter halos forming, and also beginning to see the kind of framework of, or the outline of the large-scale structure of the universe. All right, so this is a very rudimentary old simulation. The state of the art looks something like this. So if you had dark matter goggles and you could go out in the early universe and look to see how the dark matter distribution looked like, this is what you would see. So this is a dark matter only simulation. These are only dark matter particles in a box. We're starting very early in the universe, around 200 million years after the Big Bang. And this is a huge section of the universe. This is about 1 billion light years across, all right? And we put billions, well, not me, scientists have put billions of particles in there. This is someone else's simulation that I'm showing. They did a lovely visualization, so I'm using it. They've put billions of particles in this box, and they can run the movie forward. And so white bright spots are overdense regions, and dark, or what will eventually become red, are underdense regions of the universe. And so you see the hierarchical formation. Small dark matter halos collapse first, And you also see this, what was going to become the cosmic web. Underdense regions are going to empty out, so any dark matter that was here is emptying out into the overdense regions around it. You see these filamentary structures, these tubes of dark matter, so dark matter is running out of the voids into the filaments, into the dark matter halos. Let's just run that again, it's so pretty. And the dark matter in the filaments are also running to the nearest overdensities. They're running to the dark matter halos where the filaments intersect, right? And so hierarchical formation again, filaments will also merge together and all that matters. And in the center of this simulation, a large cluster of galaxies is forming, right? All right, so now that we have this amazing result, we can actually go and compare it to observations, all right? So you have all sorts of data in here. We have large scale structure, shape and size of voids, number of dark matter halos, masses of dark matter halos, and we can go and compare those to surveys of galaxies out in the universe. And so on the left is a galaxy survey. So every point, blue and purple, on the left here are galaxies out in this large, amazing map of our local universe. This goes out to, let's see, about 2 billion years, 2 billion light years out. And so you have this amazing structure, and you notice that it pretty much matches exactly to simulations. And so these simulations, these are dark matter halos, have a very similar large-scale structure. And so this is the reason why the cold dark matter model of structure formation is part of the standard model of cosmology, because it does such a great job at explaining observations of the large-scale structure of the universe. So this begs the question then, what about small scales? All right, so on smaller scales, we can begin to look in our nearby universe. So the Milky Way, our galaxy that we live in here, is in this larger group of galaxies. And this is an amazing data set for a couple reasons. So the Milky Way is surrounded by all these very low mass, faint dwarf galaxies. All right, and these dwarf galaxies are orbiting around the Milky Way. These are normally referred to as satellite galaxies. The Milky Way also has another large neighbor, the Andromeda galaxy, which has a very similar stellar mass, size, and structure as the Milky Way. It also has its own set of satellite galaxies that are orbiting around it. And then these are all surrounded by another handful or so, another set of low mass, faint, ultra-dwarf galaxies, all right? What's interesting about the local group, what's great about this is these things are all nearby, so we can study them in detail, and that's actually how we can actually discover these very, very faint objects. The other thing that's interesting about this is that these faint galaxies, remember when we were talking about the evolution of the universe in the second slide, small galaxies are among the first galaxies that form in the universe. So these are remnants of this early epoch of galaxy formation. So by studying these galaxies, we can actually learn something about how galaxies first formed in the universe. Okay, so what we want to do then is we actually want to simulate a Milky Way sized dark matter halo. So this is the dark matter halo that the Milky Way will live in. So there's this amazing high resolution simulation run by the Aquarius simulation. So as this forms, you're going to see the similar process of hierarchical formation. So all the dark matter particles in this will end up within the gravitational interaction radius of the Milky Way, the virial radius of the Milky Way. And so the small scale structure is forming first. You see the similar filamentary structure. This is all going to eventually collapse into this dark matter halo in the center. It'll tell you a little bit more about. And remember, this is the coloring here is for density. So the bright spots are very dense regions, and the dark regions are underdense. This is an amazing feat of, this is an amazing simulation. So this is one of 6 Milky Way dark matter halos they simulated. Each one performed 67 trillion force calculations. Each one is 45 terabytes in total data storage. They took months to run in human years and millions of CPU hours. So this is an incredible feat of computational power that's taking place in order to learn something about our local universe. All right, so notice that a lot of these small dark matter halos that are moving in, as they fall in, some of them are going to survive and exist today in redshift 0, but a lot of these are actually being tidally torn apart. So some of these dark matter halos fall in, they're actually being ripped apart and join the Milky Way's more smoother component of the dark matter halo. So skipping forward, this is the result we'd get at the end. This is the Milky Way's dark matter halo today, as it would look. This is a massive, massive dark matter halo. It's trillions of solar masses. The first thing you immediately notice, it's very, very clumpy. All right, and so it's actually also very, very large. It's 20 times larger than the size of the Milky Way's disk. So if we were to plop an image, the Milky Way, so this is actually an image of Andromeda, if you're careful, and if I were to scale this image to the correct size as it would fit in the dark matter halo, that's the size of the Milky Way versus the size of the dark matter halo it lives in. It's very, very, very large. It's also clumpy. And so remember when that picture of the local group, the Milky Way has all these baby satellites orbiting around it, and we know that those satellite galaxies live in dark matter halos. So some of these dark matter halos should have galaxies in them. So the most obvious thing to do then in terms of testing how well this model does in describing the Milky Way structure is to look at the number of dark matter clumps we have here and compare them to the number of galaxies we see orbiting around the Milky Way or Andromeda. And you can see that on the left, there's, if you were to count quickly, tens of thousands of dark matter halos, whereas on the right, we know of only tens, a few dozen, maybe 30, 40 or so dwarf galaxies, depending on how you're counting, right? So each of these, so this is what's known as the missing satellites problem. There's far more dark matter subhalos within the Milky Way's virial radius than there are actual galaxies that we see around us. We expect we'll find more, but we're never gonna find this many, all right? And since these galaxies should live in these dark matter halos, what we can do is we can start plopping each of these into a dark matter halo, but eventually we're gonna run out and there's many, many of these that won't have a galaxy in them. So this is telling us one of two things. Either the cold dark matter model is wrong, even though it does a great job of describing structure on large scales, it breaks down on small scales somehow, and this is an incorrect model of how structure should form in the universe. Or we're learning something about galaxy formation and that these dark matter halos do exist, they're just dark, they don't have any stars in them. So what we can do then is actually start thinking about how galaxies should populate these dark matter halos and start using hydrodynamical simulations. So these are simulations that don't just have dark matter particles, they actually have gas particles and some sort of prescription of how to turn those gas particles into stars. All right, and so if we look at dwarf galaxies, there's a range of stellar masses of the galaxies that are orbiting around the Milky Way, from the LMC, which is about 50 times smaller than Milky Way in stellar mass, to these smudges of stars in Fornax and Sculptor, and Draco that has so few stars and is so faint, I can't even tell you where the galaxy is in here. It's sort of like right about there. But still, it's impossible to tell just by looking at this, right? I had to go look multiple images to make sure that I actually knew which ones. So, and this is about 250,000 times less massive than the Milky Way's stellar disk, all right? So this is a very, very faint, very underdense dwarf galaxy. So there's clearly a lot of something going on with star formation that's very, very different each of these satellite galaxies around the Milky Way. So in that simple cartoon I showed you at the beginning, I had gas falling into the dark matter halo, it cools and forms a star. But that's not the end of the story. Stars are actually, star formation is actually a really violent process. And those stars radiate a lot of energy, and that energy impacts the gaseous environment that's surrounding that star. And so that gas is the fuel for star formation. So there's two key feedback modes that I want to think about in terms of how this can explain maybe the cold dark matter model. So early on in the universe, we talked about the end of the dark age when the first stars form. When the first stars form, they are going to heat up the gas that's surrounding them. All right? And they heat it up to such high temperatures that the smallest halos that we saw surrounding that Milky Way dark matter halo, those small clumps, are actually too small to actually be able to pull that hot gas in. The hot gas is moving too fast, and so there's not enough gravity in those small, low-mass halos to actually pull that gas in and keep it there, and eventually cool it and form stars. So this is one way that you can prevent gas from falling onto those low-mass halos and prevent them from forming stars. The other way, this is a simulation of a dwarf galaxy. So this is what you see here. This is a simulation of the gas. I'm going to hit play in a second. So magenta, the color of the gas indicates the temperature. Magenta is cold. Green you eventually see is warm gas, and then red is hot. Eventually this is all going to turn green. This is when the first stars reionize and heat up that gas, and immediately, quickly, all the gas is going to heat up to a higher temperature. So I'm going to hit play. So hierarchical formation, you see these things begin to form stars. Boom, reionization happens, heats all the gas surrounding in the surrounding volume. And then eventually, you're going to see these bursts of gas being blown out of the center. There's a galaxy in here. There you go. So high mass stars are very energetic. They drive stellar winds, but some stars also die in supernova, which we heard about in the first talk. Not only do they produce elements, they also drive these strong winds that blow a lot of gas out. And so by blowing gas out, what they're doing is removing some fuel for star formation. So even though this continues to form stars, stars continue to die, you continue to see explosions, there's a lot fewer stars would form in this galaxy than there would if it wasn't for these violent star formation feedback events. All right, it's a beautiful simulation. I'm going to keep going for time. All right, so here is an image of a simulated Milky Way galaxy. This beautiful image of the latte simulation done by Andrew Wetzel and collaborators. This is an image of a disk of the Milky Way. The dark parts are a gas in this simulated Milky Way disk. And so if we do a full hydrodynamical simulation of the Milky Way, and then we were to go and count the number of satellite galaxies we see orbiting around it, and compare the abundances and the stellar masses, the blue line is the simulated galaxies, and the black lines are Milky Way and Andromeda. And you can see that the simulation does a good job of accounting for the number of satellites we see around both these galaxies within some scatter. And so this is a way that galaxy formation can get around solving this missing satellites problem. However, there's alternative models of dark matter. This is actually what I work on. Particle physicists are clever people. Just come up with one particle model for dark matter. They came up with many, many. All right, and so in the standard model, we think of dark matter as a WIMP, which is cold dark matter. And early on in the universe, those dark matter particles gravitate, mutually collapse into dark matter halos. And the first things that form are these small, low-mass dark matter halos, right? Well, there's other dark matter models. One of them is a sterile neutrino. Sterile neutrino, which is a class of dark matter known as warm dark matter. These are lighter particles and they have larger velocities. And so what happens in these particles, instead of, if you think of two particles at rest and just nothing but gravity, they're going to actually move in and gravitate, right? But if you have some large velocity, which we have in the case of these warm dark matter particles, they can actually just free stream right past each other. And so what would have collapsed in cold dark matter won't collapse in warm dark matter. And these velocities prevent the formation of these small, low-mass dark matter halos forming in the early universe. And so in cold dark matter, if the hierarchical formation picture looked like this, small things form first, build up larger and larger halos where our dwarf galaxy will live. In warm dark matter, those small ones don't form. Warm dark matter, and depending on the details of the particle model, it's too much to get into with the 15 minutes I have, does form hierarchically, depending on the details again. But the first things that form are a lot more massive and will eventually grow to the halos that host the dwarf galaxies through fewer mergers or through just smooth accretion of the dark matter that's around it. So then if we simulate the Milky Way, the dark matter halo that will host the Milky Way in cold dark matter, you see this clumpy structure that I showed you before. But if you were to resimulate this in warm dark matter, and here's my simulation on the right, you see that it's much smoother. Much fewer dark matter subhalos formed. So there's a lot fewer clumpy substructure on the right. And so basically what this says is in this case, instead of a lot of halos being dark, each of these almost all of them will host a dwarf, all or most will host some galaxy in them. All right, so we have a different accounting then of how galaxy formation proceeds in warm dark matter. And if we run hydrodynamical simulations of dwarf galaxies and look at the star formation histories. So this is the cumulative stellar mass that accumulates over the lifetime of a dwarf galaxy. So the rainbow color of curves are warm dark matter galaxies, and the gray curves are cold dark matter. What I want you to take away from this is that for the most part, galaxy formation proceeds similar in warm dark matter and cold dark matter, with a few exceptions. So one prediction from this suite of simulations that we ran are that two of these galaxies should form most of their stars or all their stars in the last 2 to 4 billion years. So these are incredibly young, very faint dwarf galaxies that will form in a warm dark matter model, which we don't expect they'll form in cold dark matter model. So this is one way with larger surveys that are upcoming with these new generation of telescopes and more detailed observations of dwarf galaxies. If we were to go out and find a very faint, very young dwarf galaxy, it would tell us that a warm dark matter model is actually favored over a cold dark matter model. All right, I'll just leave up my summary and say thank you. So the question is do we have an idea of how much dark matter is on our own planetary system? Yeah, so because because our solar system is in the spiral in the disk of the Milky Way galaxy, about halfway out, and that Milky Way galaxy exists in this dark matter halo that's basically a gas of dark matter particles, and I told you that millions of dark matter particles are passing through you. We have an idea of what the average density of dark matter is in our solar neighborhood. And I'm totally blanking on what the exact number is. Do we know in the back?
Jeez, Brandon, gosh.
What is the average density of dark matter in our solar neighborhood? Yeah. No, it's a great question. I should know that. We will do an edit to the YouTube video. Our video editor will post it up. So, but yes, there is some sort of average density in there, and so there are lots of dark matter particles that are as our star passes through the sea, they're streaming past us. Yeah.
Up in the balcony.
Can I elaborate on the last plot? Okay, so what exactly is happening at the top and what exactly is happening at the bottom? Okay, so yeah, I kind of blew through this slide. I basically just wanted to call out the fact that there's these outlier galaxies in a warm dark matter model and one type of warm dark matter model. Okay, so what's happening in this case is, so 0 is the Big Bang and we're over here at 13.7 billion years. So early in the universe, these galaxies are forming almost all their stars. So this is before reionization sets in. These galaxies form a ton of stars, and then that reionization either shuts down the galaxy formation or a combination of some sort of supernova burst blows out the gas, and because the reionization, these dark matter halos are so low mass, and reionization heats that gas up, they're not able to accrete more. So what this says is 100% of the stars form within the first 2 billion years, and then that's it. It's shut off. So all the stars in this cold dark matter galaxy in the gray, or this warm dark matter galaxy in this orange curve, form very, very early, and that's it. They don't form any stars afterwards. So these are kind of these fossils of early star formation that that are possibly orbiting around in our Milky Way. And so we see galaxies like this that have pretty much all their stars very early on and then shuts off, right? The ones in the middle are ones that continuously form stars over their lifetime. It's kind of like that simulation I showed. They blow out some gas, shut off star formation for a little bit, it falls back in, form more stars, keep doing that. It's this breathing mode star formation. And then in the end, these are galaxies that have managed for some reason to hold on. They're kind of at this knife edge in the galaxy formation process where the dark matter halos have managed to accrete and hold on to this gas, but they haven't been able to cool it and form stars until very, very recently. And that's actually because the ionizing background, the background UV photons that are heating up, that are ionizing the gas in the early universe and heating it up, actually has a peak and then it comes down in the recent universe. So the strength of the UV background has dipped enough that this gas is no longer maintaining its temperature and is actually able to cool and begin to form stars. So these are galaxies that somehow managed to hold on to the gas even though they didn't form stars, and are forming everything now that the gas is cool enough and able to collapse and form stars. Does that answer your question? Okay.
Good job, Brandon. New question, here you go.
Generally accepted lambda CDM model of the universe, meaning that we're moving toward a lambda WDM model of the universe?
So the standard cosmological model that I mentioned at the beginning is generally referred to as the lambda CDM. So lambda is the cosmological constant, the vacuum energy, the dark energy component, and CDM is the cold dark matter component. So does this mean that we're moving to a lambda warm dark matter model? And that's exactly what this is. So this is a lambda warm dark matter model. We have the same dark energy, the same vacuum energy, and we've specifically chosen this model such that the velocity wipes out some of that small scale structure, but it doesn't wipe out the large scale structure. So if you look at that first simulation that I showed you, it should look identical in warm dark matter and cold dark matter. So all the successes of the cold dark matter model on large scales are preserved in this warm dark matter model. It's just the only thing that is different is these small galaxies that form early on. They form form a little bit later and have a little bit different star formation histories, and they form fewer of them. So this has implications for high redshift observations. So James Webb Space Telescope, when it goes out and looks and counts the number of galaxies in the early universe, should actually really be able to tell us a lot about which one of these two models is correct. If we see a lot, then it's cold dark matter. If we see few, then maybe warm dark matter is a better explanation for not only stuff nearby, but also at the high redshift end.
Oh, more questions. Last question right there behind.
So, is it possible that both models could somehow be right?
Is it possible that both models could be right? Great question. Yes. So the simplest thing is to start with one type of dark matter model, look at what galaxy formation looks like, what structure formation looks like, and just stick to that. People have considered mixed dark matter models, so a little bit of warm, a little bit of cold. There's a whole range of dark matter particles that exist, and they have all different types of properties. There's, Brian has talked about ultralight axions, and that's a certain type of dark matter particle that has this kind of weird quantum pressure that prevents stuff from clustering very close in. I actually looked at a model using these ultralight axions and cold dark matter and see what type of fraction you need to see any differences from cold dark matter. And the answer is you need quite a bit of non-cold dark matter to see strong differences in the structure formation. However, really, if you think about the how nature produces particles, there's a whole range of wild number of particles, and supersymmetry actually predicts a ton of different particles of different masses and properties, and string theory, or whatever the next higher level model of particle physics, it's possible that there's many different types of dark matter particles. That gets a little more complicated and it gets a little bit harder, and so the easiest thing to do is just start with one and then add more as we go on.
Great. Let's thank AstroBoz.